Thank you very much, Adam. Well, it's been a great start to the conference. We've had a couple hours of a good introduction to digital twins, reminding ourselves of some of the important features. Today's panel that we're going to talk about, as you introduced, we want to dig a little bit deeper into how digital twins help us with implementing machine learning, machine vision, and AI. So I'll quickly introduce our panel. We've got Andrea Kors, a venture principal, Shell, dialing in from very early morning Houston. We've got Julian Zek, Senior Program Manager, Optimisation, Maersk Drilling from Norway. We've got Michiel van Haersma Buma, VP of Customer Success from Akselos in Amsterdam. And right now we have Debasis, Bisoi, VP, President of Manufacturing Digital and IoT Solutions, Tech Mahindra, calling in from Bangalore. So welcome, and let's kick off right away and get into the topics. So Andrea, what can you share with us?
Yeah, so let me first do a quick introduction. I am Andrea Kors. I work for Shell Ventures, the venture capital arm of Shell. So what that means is that we invest and we work with entrepreneurs and startups to scale up ideas. Shell Ventures looks for technologies and business models that could help us accelerate the energy transition and that have an impact, a material impact on our costs. We invest in areas like oil and gas, but also we're looking for, renewable energy, like wind, solar, energy grid, and also the future of mobility and decarbonization. I personally focus on the areas of robotics, machine learning, artificial intelligence, and decarbonization. So I'm looking forward to the panel.
Great. Julian, how about introducing yourself and give us a brief intro?
Yeah, my name is Julian Zek. I am Digital Portfolio Manager for Maersk Drilling. I'm mostly working with maintenance optimization and digitalization of asset management. In my past, I have been doing the similar things for NOV, FMC, and Schlumberger, building both systems and analytics, so everything from physical models to data-driven models, and also integration between IoT and management systems. I also have a position as research fellow and on Norwegian University of Applied Sciences, where I do research within cyber physical systems.
Okay, great. Michiel.
Thank you for kicking us off, David, and hello, everyone. My name is Michiel, and I'm the Vice President for Customer Success at Akselos. We're a software company that builds digital twins for structural integrity applications. So examples can include offshore wind farms, large oil and gas structures, and smaller equipment like pressure vessels. And our digital twin is physics-based, so we're a little bit different than artificial intelligence and machine learning type of approaches, in a sense that we calculate outcomes based on the laws of physics. So to give you a very simple example, suppose we're trying to predict where a paper clip will break when you bend it back and forth. Then an AI ML type of approach could look at hundreds or thousands of videos or data sets to predict where that will happen, and our software will actually calculate based on properties of the paper clip and the forces that exactly are applied to it, where it will break down to the millimeter. Now, I think in the context of this example, it's of course irrelevant from a value perspective. But if you were to apply that approach to a really big offshore structure like an FPSO, the stakes will be enormously higher, right? So there you really want to understand what happens down to the square centimeter, and that's what we focus on. The company is heavily focused on the engineering side.
Okay, Debasis.
Yeah, thank you. Good morning and good afternoon, everyone. This is Debasis from Bangalore, India. I work for a technology company called Tech Mahindra. I guess I am the odd one out here in the sense that we don't implement digital twins for ourselves, but we help our customers implement digital twins. So I do have some experience, some learning over the past few years since digital twin has become a very important topic. Happy to be on this panel and share my experience and learnings and learn from you as well. Thank you.
Okay, good. Why don't we go ahead and move on to our next topic, and sort of building on what you've each said, it'd be interesting to hear from you the idea how digital twins might evolve to make use of the insights from machine learning, from AI. So, kicking off, Andrea, on that. Do we see people doing this? Do we see people saying, okay, yeah, I got something physics-based like Michiel mentioned, but I want to also train that and implement some kind of a learning into that?
Yes, absolutely. So I guess first of all, Akselos is one of the portfolio companies that Shell Ventures invested in. So we're very proud of having them as one of our portfolio companies. And Michiel used to work for Shell Ventures, so I just want to put that out there. I guess that what I would like to start with is the definition of digital twin actually means different things to different people. So I just want to start by saying what it means to Shell, right? So a digital twin, the way we see it, is a digital representation of the physical elements of an asset and its dynamic behavior over its life cycle. What that means when I say digital representation of a physical asset, right? A physical asset could be used very widely. So it could mean an individual piece of equipment, or it could be a plant, it could be a site. So in other words, it could be used for assets of different size and complexities, right? So we're looking at maybe a valve, or we're looking at an FPSO, like Akselos would look at. So furthermore, we're saying, okay, we're looking at a digital representation. So what does that mean? So we're creating an electronic replica of these physical assets, and we're looking at the behavior over the lifestyle. Now, when I say that, it means it could be historical, it could be current or real-time status, or it could be futuristic, right? So you could actually predict the behavior of these different assets, right? So that's why digital twin can be so difficult, right? And it takes this integrating data from multiple sources. So you're taking information from tools, from applications, from documents, from technical references, in the case of Axelos, from actual physics. And then with that, you do describe all the different facets of the asset, the configuration, the history, the operation, and then the predictive behavior of that asset. So you can see how it could be a complex process. The AI takes part and the machine learning takes part because when you have big amounts of data, right, it's easier for a computer to learn and to help you identify patterns that you may miss otherwise. So in the case of predictive analytics, I think AI will play a big role.
Good, thank you. Julian, you mentioned, you talked about maintenance. That would be interesting. We have a physical, a digital twin model of some physical process, but during maintenance, we find out that different things are happening. We're getting more vibration, we're getting more wear, things are happening that we'll see from maintenance. How does that get fed back into a digital twin to be better?
The thing is, how I see it, that the future, any future system, which strives towards kind of reasoning or reflexivity, it can be control system or it can be maintenance system, as you mentioned, will require some kind of hybrid approach, as also Andrea points to, because like in maintenance, we need to keep this physical part, and where I agree with Michael also, but the the issue here is that amount of and complexity of the processes is so huge, amount of data, level of noise is so big, that if we are going to build physical models for all of that, we will never be finished. It will eat all our human infrastructure and financial resources. And that's not just to solving our issue of maintenance, it's also how we acquire data, how we sort data, how we ensure data quality, and how we do the reasoning in the end. So digital twin as an entity which can put all these things together, over the longer period of time is an essential tool for us here.
Okay. Michiel, you guys have a really impressive software for modeling. I've seen some examples of an FPSO hull and seeing, predicting the stresses and strains and the fatigue in that model, physics-based model of the hull. What happens when we go in and we inspect somewhere and predicted to be a high fatigue area and we don't find anything? How do we learn from that? How does that get fed back into your models?
Sure. So that's a good question, David. The way we've designed our software is that it can integrate into your existing workflows. And that means, if you have fully automated inspections like drones or robotics, through open APIs, we can load that data into our digital twin. It will analyze down to the square centimeter where you have high stresses and what the inspection data is telling you. So it might say, for example, hey, we've now actually detected the wall thickness has declined more than you had anticipated, and as a result, actually your fatigue is and your high stress areas have changed, and you need to reprioritize your inspection. Right? You don't want to be inspecting tank 3, but you need to inspect tank 7. Because that's now due to the change in stress profile. That's where your biggest unknown currently is, and the biggest risk area, because you might not have inspected it for very long. So we can integrate with manual data, inspection data, but also with automatic feeds. And what we've done for one of our customers off the coast of Africa is doing a combination of that, right? So you have the inspection data feeding the digital twin and then automatically generating new recommendations on inspection planning. And what's, I think, a differentiator there, that existing simulation technology doesn't have that capability, and that's down to granularity. So typically you'd need to generate multiple submodels to get to the right level of detail. And what we provide is that full detail, but at the entire scale. So if you look at the topic around revolutionizing the current model, I strongly believe that revolution will be led by the integration of physics-based modeling into AI and machine learning. So I think to a large extent they're complementary. So as an example, I think one way you could combine the two is actually by using physics-based models to generate thousands of what-if scenarios that simulate failures, say, of a jacket structure or an FPSO. And you can use it as a training set for machine learning, right? Because that gets better as you have a larger training data set, and the amount of failures is not always abundant in offshore operations. So I think they're very complementary, and that's just, I think, scratching the surface of what's feasible when you combine the two approaches.
Yeah, I like that concept. In the beginning, start of operations of a facility like this FPSO, you don't have a database of information, so you can pretty much only rely on the physics-based kind of models. But as you build that data from all the different IoT devices, stresses and strains, vibrations, mid-ocean conditions, dynamic motions of the FPSO, it's great to feed all that back into your model. So I think that's a good feature. Debasis, you're helping your customers with digital twins. We have mathematical things that might come out of a digital twin, but the customer has a view of his physical understanding. Is there really a correlation that when I set the timing of a valve closing in a certain time limit that it was causing some pressure surge? So physical understanding versus what math is telling us. How do you help your customers navigate through that with their digital twins?
Yeah, so David, thanks for the question. There are two elements that I would like to bring out, right? So any asset, um, it is first designed, and then it is manufactured, and finally it is actually used in the field or in its targeted scenario. See, what we have seen in our experience of working with customers across many sectors is that they derive the maximum value when they actually establish digital continuity across uh, you know uh, twins of the asset at different stages of life. So there is a twin of the product at design stage. So let us call it the design twin of the product. There is a twin of the product when it is being assembled or manufactured. So let us call it the manufacturing twin. And then finally, when it is being used, right? So that is the operationality of the product, if you will. Um, what we have seen is that you get better insights and better inferences if you collect data across these multiple twins, right? That is when the simulation and modeling actually becomes much more accurate. This is one aspect. So in that sense, we actually advise many of our customers to undertake integration programs across these different life cycle stages. So that is one element, which is the continuity element. The other element is, as operated or field data, taking that and collating that with the reality of life. We still have many customers, and you'll be surprised to know that there are customers in very sensitive domains like aerospace or defense, automotive, so on and so forth, where the mission criticality of the equipment is very, very important. Still, in many cases, in some low risk equipment, they actually run it to failure before undertaking any maintenance activity. So essentially, it is about maximizing, the value of the part or assembly or the equipment, if you will, before any maintenance is carried out. In many of those instances, the mathematical models tell us something very different. The mathematical model would predict that you have to replace this item right now, or you have to carry out preventive maintenance right now, so on and so forth. But based on historical extension programs in aerospace, it is called extension program, and I'm just trying to put that concept out here. uh, People have been very, very successful in running equipment to failure, and then in certain cases it actually makes more sense. So my point is, one is you get better insights by integrating the twins across different life cycle stages of the product, and not just at operational stage, which is what mostly we have discussed here. The second point is, in some cases, the customers have been able to take field data or operational data and then make meaningful changes to design so that the product actually behaves much better, right? So um, the findings from the field, the algorithmic outputs, and real life experience need to be seen together is the key point that I wanted to make.
Yeah, I like that. There's some interesting statistics about how much of maintenance. It's an incredible statistic. It's like 70% of maintenance is done at the wrong time, too early, too late. The wrong maintenance or whatever. So the idea, we start out, we don't have a database about the performance of the asset, but we have some nominal time periods. After so many hours, we want to change something, and if we just blindly change it at those time periods, it may be too early. But if we've got the benefit of a good digital twin, if it's been feeding us back the real time data from the operations and tell us, well, actually this thing hasn't experienced some of the design loads or the as much fatigue from a model as you might have expected, and you can extend your maintenance period. Those are tremendous values to be captured. So that's a great point. We're doing really good on time. Before we jump to another thing, I might come back and ask a sort of a random question of Andrea. We haven't heard that much so far about AI. We hear a lot about machine learning. How does AI come into all this? How do we build on the physics-based models, the machine learning? How does this progress into AI solutions?
So I think you have to look at the digital twin dimensions, right? So I think Debasis also mentioned that you have, the way I see it, you have three different dimensions when it comes to a digital twin, right? So you have your data, you have the visualization of that data, and then you have the modeling of that data, right? And I think so a prerequisite for creating a good digital twin is accessing the data at the right time, accessing the right quality of data, and making right decisions with that data, right? So AI has a lot to do in that part with cleaning the data and making sure that you train your models to actually, become capable of consuming these very complex data formats that are coming from very diverse data sources. And then, when you look at the visualization, then it's just to make it easy to understand and consume for the users, right? So it could be 2D, 3D, it could be AR, it could be VR. But the more mature the digital twin is, the more realistic it becomes, right? And then where AI comes into place again is in the modeling part, right? So as I mentioned before, the ability to provide predictive analytics and good modeling capabilities, right? You should be able to use the data that's available to understand the past behaviors of the asset that's being modeled in order to predict the future behaviors of that asset. And then you can actually optimize, right? So when we talk about optimization, then again, we can look at, okay, what have we done in the past? And I think where it's critical and where there's still some sort of disconnect is between this data analytics and the data modeling, because you need to really understand the failure modes of an asset, right? So you need to understand, well, if we're looking at a valve, right, like you were saying, what happened the 5 past times that this valve failed? Can we look at that data and see exactly what was happening, an hour before, or 3 hours before, or 5 months before? Is there any way that we can then look at this failure mode and understand when it happens before it actually happens? Because when things fail, it's very costly, right? Especially if they happen offshore, for example. So it's really utilizing this capability and AI, but a model is only as good as the data you put in. So I think, the issue is with anything in digital, any digital initiative, right? That the biggest challenge is to get reliable access to clean, accurate, and consistent data, and AI can help with that. Go, Michiel. I see you raising your hand.
Michiel.
Yeah, thanks. So I was keen to respond to this point and the one that Debasis made earlier. So I think a really important distinction here to make is that mathematical insights from AI themselves do not provide physical understanding, right? So to a reasonable extent, AI is kind of a black box based on an input-output relationship, and it doesn't necessarily understand the underlying physics, right? So in that kind of situation, the math doesn't translate into physical insights, right? Particularly if the data set is limited, say, in early asset life, and you don't have a database of failures. And that's not intended to criticize AI in any way, right? It's simply to point out that I think for true physical understanding, AI or machine learning will have its limitations due to the way it is set up. And I think the upside there is, of course, that AI is really easy to implement, as well as machine learning, using whatever data is available versus a physics-based model that requires accurate design input data that can sometimes be hard to come by, right? If you're looking for data for an asset that was designed 30 years ago, that can be a challenge of its own. So I think, AI and machine learning can be great for challenges where data is abundant and where physical phenomena aren't as prevalent. Maybe it's about optimizing a separator process to maximize throughput. But then I really believe you need physics-based models to provide to give you value by really understanding root causes of issues, right? And understanding where you might have cracks forming, might have excessive wear, and that I think really will then allow you to drive improvements on things like predictive maintenance.
Yeah, it's interesting, this idea of physical understanding, trying to get our software to provide some of the capability that we had from experienced humans before. The idea, like Andrea mentioned, something might have happened 5 months ago that's now led to today's failure that nobody noticed at the time. The idea that you exceeded an operating integrity window of something and you shortened its lifespan. So now you're having a failure, but everything's been fine for the past couple of months, but it was something in the past that happened. That's something that humans might have looked for, is what's the operational performance of a piece of equipment? What's happened in the past? Why did it fail today? And get our systems to be able to similarly look for that kind of indicators within the data streams. Julian, do you have anything you'd like to add on the AI angle of this?
Yes, I would just like to comment on, because we are also here in a kind of definition question. What do we define as AI versus machine learning? From my perspective, machine learning is a tool within a set of tools, which actually is artificial intelligence. But artificial intelligence is a kind of intelligence implemented within a machine, not within a human, and using different tools from the set. For example, it can use physical models to do reasoning. It can use machine learning set of tools to perform parts of that reasoning, or it can use statistics or whatever we want in it. So I think that to cut AI from machine learning or any other modeling is a bit difficult, and because the borders are very blurry here. All of that what we talk about is part of AI, and I think that later in this session we will talk about relation between human and artificial intelligence, where also that border becomes more and more blurry within.
Okay.
Yeah, if I may just jump in, I fully agree, Julian, because I think you can't separate, and I think it all goes back to the definition of what is AI, right? Because just like digital twin means different things to different people, I think AI means different things to different people, and we need to realize that it is as good as the people that are making the algorithms are, right? And it will take a lot of inputs. So when we talk about physics-based models, they can also be physics-based models in AI, in the algorithms themselves, right? Because in order for you to understand the failure modes, you need to have that based on something, right? The way I see AI, it's actually putting all of that together and then allowing the machine to learn, right? So it does get a little bit confusing because you have the physics-based models that then become, machine learning, that then are called AI. So it becomes a complex type model, but I think we're all saying the same thing.
Okay, good.
Yeah.
Well,
if I may add just one point here, David, I think Michiel made a very interesting point. See, data is actually very crucial, right? And Andrea also made the same point a while back. We have seen is data is generally very, very scarce for old equipment. Data is also, not available for new equipment, right? So if you are launching something new into the marketplace, you don't have data because there is absolutely no operational history for the equipment available. So in both the cases, we have seen instances where customers have been very successfully, at least optimally, been able to implement digital twins by means of, let us say, hypothetical data sets and different degrees of hypothesis testing. That is where again, very, very handy, because you have one data set using which you have trained your algorithm, but then you don't have another data set on which to test it upon, right? So this can become very, very tricky, right? And people have actually improvised in very, very, very many different ways to circumvent these kind of situations.
Yeah, that's a good point. We actually, I've neglected to remind the audience, if you want to, please put some questions in the Q&A section on the stage Q&A. And we actually got a good question a few minutes ago. What is it possible to implement AI solution without historical data? And Debasis, I think that's what you're alluding to. We certainly have a database. A supplier of a piece of equipment, a valve, would have a database for his equipment, or water treatment equipment would have a database. And so we have sort of a historical database of that type of equipment or component in other users, other applications, which may not be exactly the same as our specific use, but it's a good way to start before you do build a database. I wanted to go on to our last topic, best practices for reducing digital twin project risks, lessons learned. And Andrea, how do people, what kind of lessons have people learned, and how have they applied that to do better putting digital twins in, do you think?
So lessons learned. I think I've mentioned it in my comments before, but I do think that the key is the quality of that data and ensuring that data that you're using in your models is good, because you've heard the expression garbage in, garbage out. So you could create, if you're not careful, I think the problem we have in our industry is actually that we have sometimes too much data. And this is data that has not been properly cleaned, that is not properly understood. If you think about the amount of sensors that a company like Shell has, we have thousands of sensors that are monitoring the equipment in our wells, in the refineries, in the chemical plants, and we don't yet have the machine learning models developed to detect and prevent downtime. So I think it's just, we are definitely working on this, right? Because there's a lot of stuff that can be done, but it's just turning that data into insights, right? It's not just about having data. The best way I can explain it is like when you go to the doctor and you get your lab results, right? And it shows HGL 27, right? That's a data point. And that's what we have a lot of. Right, but it's like, what does HGL mean, or HCl, and what does that 26 actually mean? Is that good? Is that bad? And then once you get a range, well, it should be between 15 and 30, then okay, well, that's fine. But if it is over the range, then how do you solve it? How do you reduce it, or how do you increase it? And that's what I mean by data insights, right? When the doctor says, oh, I'm looking at your results, your cholesterol is high, and you need to take these steps in order to lower it. We're not there yet. And I think that's what the whole digital twin and what the industry is trying to do is, can we not just get information back, but understand how to use that information in order to optimize the operations of the company?
That's great. Julian, how about lessons learned and how to do better at putting in digital twin projects?
I think in my experience, the crucial thing with building digital twin, any advanced analytics, is to have a right and defined goal, what you want to achieve and why are you doing it, and that you have correct and precise milestones between now and then, when and how you are going to come there. And that is leadership. It's not a technical issue, it is leadership issue, because from leadership perspective, digital twin is not only a technology, it's also a commercial object. So that commercial object have to achieve certain goals. And if these goals are not defined, it is extremely easy to lose tracks, and start developing anything. And that's pretty fine for academic institutions, but not for the commercial actors as us. We need to, for every investment, we need to create any value. We need to solve the problem. We need to solve a need, not create a new need again. So in that moment, when the strategy or my plan is defined, that executive level or leadership level have to move themselves off the way and give the front seat to the people who know how to do this. Not keep digital twin or advanced analytics at their own playground or advanced computer game, which I have seen many times, that they still want to change things and they're still doing things and making things out of and confuse people who actually knows or scare them off to do their things, And the last lesson learned, is, we need to understand that reporting for the digital twin is not quarterly reporting. You can't. We invested 100,000 and we got 200,000 out of the digital twin. You need to have a long perspective on this. It's a strategy choice. It's not like something which you build to show off for a short period of time. Because it will cost you a lot. It will cost you to maintain a lot, and it will create you value down the road.
Yeah, that's good. No, this was we haven't mentioned culture up to now, but there's a statistic that 70% of pilot programs fail because companies didn't do anything about the culture side. So they had a great tool and it was nice and shiny and the people using it were great, but with people making hierarchical decisions from far away that wasn't timely, we weren't really getting the benefit from the digital twin. So it is about agile, multidiscipline teams close to the asset using these tools to get the most value out of them. Michiel, how about lessons learned?
Yeah, thanks, David. So I think the points Lee Hodder made in his keynote this morning were actually spot on, and the two that stuck with me in context of learnings were being outcome focused, and Julian just mentioned this as well. This one as well, I think, is super relevant. And the second one was around partnerships and collaborations being a must. And I think part of that is related to mindset and culture, as you just alluded to, David, which is always a hard thing to do. When you've worked long in a company, I think sometimes it's hard to look outside, but no one knows it all. I mean, at Akselos, we are extremely proud of what we developed. And at the same time, I think we realized we really need to work together. Maybe to give you an example, because I think that really opened my eyes to some extent. We were initially we developed a digital twin for one of our customers to assess the remaining fatigue life of this floater. And suddenly, during one of the meetings, we started talking about how can we apply this further for predictive maintenance. And someone mentioned they were going to fly a laser scanning drone around the asset. And what we're now about to do is use that data from the laser scanning, incorporate that directly into the digital twin. We process the data and we can actually pinpoint areas that we would need to inspect at a more detailed level for wall thickness using ultrasonic, for example, right? And then there's so many workflows to then deliver value for the asset. So I think, when you implement this, the culture mindset should also be, I have some business cases in mind, but I will also be learning a lot as I go along in this journey because of, there's just so much opportunity out there. It's hard to map that all out at the very beginning. So I think maybe as a second lesson would be about, start now and deploy your twin across the entire life cycle. So using it to optimize your design and then using that design to determine where you need to install sensors, etc. And subsequently using that in operations to define, where you need to do maintenance when assessing brownfield modifications. And I think ultimately also then assessing, what you need to do to extend the life of the asset if needed. So, that would be some of my lessons.
Yeah, I like what you said about we don't know everything in the beginning. We're going to learn stuff as we go along. So we may find out we have too many sensors in one place and not enough in another place, or we've got a bit of pipe that we're not measuring the vibration of, and that's causing us a problem. And so we ought to put a wireless sensor there. And so there's lots of stuff you'll gain, lots of knowledge you'll gain during actual operations to keep tweaking where you get data from and what you make use of that data. Debasis, lessons learned.
Yeah, thank you, David. See, a couple of points, and what I'm about to say is not very different from what Julian, Michiel, and Andrea have said already. See, you will be surprised to know many large and forward-thinking organizations, they don't keep all the data, right? There are times when they throw away data. So this is one expensive lesson we have learned, that do not ever throw away any data that you have. You have no idea when it becomes useful to your digital twin initiatives. That is one. The second is still 2D definition of a product at a design stage is very, very common, right? While digital definition is being adopted at design stage progressively, a lot of products still have their two-dimensional designs right there. There are drawings, physical drawings of the designs of products, and a significant amount of investment needs to be made into digitalizing those drawings, which then form the baseline for the digital twin at design stage of the product. Last but not the least, I think this has already been echoed already. Digital twin is actually a journey, right? So it is not an end state in itself. It's a very, very progressive undertaking, and for large and complex digital twins, one needs to be very, very patient. So that has been my learning from this endeavor, David.
Okay, good. Yeah, I like the your story about the throwing away data. Actually, at some conferences, people come up to me and say, "Oh, we have too much data." Well, perhaps they're not making use of it.
If I could just add something to that. I actually just read a report last week about sparsity, which is what the human brain does, right? Humans do not remember every single thing there is to know. They just know what's important, and they take that. So AI is trying to change into that sparsity model to mimic the human brain, where models should not know everything possible, but just understand what's important to know, right? If you think about your day, you don't remember every single second that happened during the day, but you remember the important things. So how can we make AI models behave more like human brains is what I think the next step is going to be. So I actually think that it's not about getting more data, because I do think that we're inundated by data. It's all about understanding what data is valuable and what data is not.
Yeah, and sometimes that data is the wrong fidelity. So people have too much data, and they were recording something every minute, and actually for some kind of voltage surges, you needed stuff on milliseconds to try to diagnose a problem. So to have your system set up where it knows when it can have infrequent data collection and recording and storage versus when we need to start getting more frequent, increasing the fidelity of data around a suspicious event. Something starts happening and we want to start getting more data to see, is this something we need to worry about or not? We've got another question. I'll throw this out to anybody in the panel. There's been some recent progress in physics-constrained deep learning. I believe such a hybrid approach will be the future. Do you have experience or looked into this? Has anybody worked with physics-constrained deep learning? Yeah, I don't know. I mean, I like the story that you might see an insight from a bit of data that's telling you, oh, you got a problem, but physically that's impossible. So that's a mathematical anomaly that's come out. So you have to ignore some of those things. You're going to get a certain amount of noise come out of some of your advanced analytics, which may or may not have a physical based explanation. Michiel, we might detect an area where we think, we're expecting to have fatigue, but we don't have it, and it's actually because somebody used a different thickness of steel. They built up the weld profile differently. Something's happened to improve the situation. So the physics prediction, it's not wrong. It just needed to have better data.
Yeah, so one of the things projects we've worked on that touches on this topic a little bit. I don't know if it formally classifies under the deep learning, but is around flight path optimization for drones. So it's a little bit outside of the oil and gas scope, but I think the story is interesting. So when you fly drones, they often develop, they have a certain targeted mission, but they might get damage on their wings due to small collisions or whatever. And you want to be understanding, in real time what that means in terms of the probability that the drone can meet its mission. So you want deep learning you need the deep learning to analyze, what kind of flight paths can I take, but you need the physics-based piece to understand, does my drone actually survive? So what we've done there, and it's a case we did together with MIT. I'd be happy to share it with whoever was interested in this. But what we were able to do real in-flight path route optimization using physical insights, but having the power of deep learning to really determine, hey, what is exactly the best route to still complete the mission, right? And I think if you draw the analog to oil and gas, I think, let's say you have a floater and you have damage on certain, it's an older asset, but it's suddenly been hit by a boat. So you've got a dent, and now you want to analyze, hey, what should I be doing going forward, right? And I think deep learning there could help you assess, hey, if you now, reduce the loads on the left part of your structure, you might actually make it another 10 years versus if you, keep using the crane heavily on that side, you might actually have to decommission the platform in 5 years. So I think, they're very complementary to a large extent. But I'd be happy to talk more offline with whoever asked the question.
Okay, good. It's in the Q&A on the stage. So we've come to the end of our time. I want to thank each of our panelists for sharing some of their insights and being with us today. I think it was a good addition to what we've heard earlier this morning, and I look forward to the rest of the conference. So if I could go ahead and hand back to Adam, and thank everybody for joining us.